3 or 4 faculty who work in the micro nano devices section together with all our needs combined. We don't run separate labs because our needs are very integrated. So we have one lab where everybody works in cohesion. Even our graduate students are not really, they cross-pollinate. Obviously everybody has an advisor, but they need to learn the protocols and the tools together. So this is a gowning area. We are still in the building phase and moving equipment from Stocker to here. So you will see maybe half of what we have. In fact, we have some larger pieces of equipment which are on the, some of them are ordered coming up, some of them to be moved from Stocker. So let's enter with 8 of us together first. Can you close the other door? So this room, this facility is a positive pressure. We are always pushing air outside. We're not letting air in. The building is, there's 27 of these filters. So if you come in here, so what you're seeing is actually the largest room. This looks like a corridor, but this is really the largest room in the facility. So we have other rooms on the left and right. So over here, our first process is in this room. If you come in, you can spread out along the, so basically this room, as I said, is still, we have unpacked equipment, some of the tools. You can come in, just stand back, you can come in this way, it's safe. So in this room, we do hot and cold processes and some of the electrochemistry. I have electrochemistry set up where I do some specialized material processing with a wire bonder behind you. That wire bonder makes that gold wires connected from the chip carrier to the chip. You have taken the packaging with lectures. So chip is standing along perimeter of the chip holder and the edge, and you need to use gold wires to connect, so that does that. We have some ultrasonic shakers and some other equipment, but over here is the equipment we want to show you today. What you're seeing is inactive. If you, in fact, if everybody sees the red glow, that's because inside this, how many degrees? 950 degrees right now. Then this can go up to easily 1200 degrees. And when you, when you put the, you see the boat here?
There's a ceramic boat here with some of the silicon wafer samples. Silicon wafers you have been already familiarized with. So we will, in the later process, we will actually show you how to clean and dice them from a wafer. But because this step takes a little time, so we will start off with this. So in the boat you have like some silicon wafers, and then what I'll do is I need to open this up, I'll push it in, and then I will connect it to oxygen. So then the first step, which is the oxidation step, will start. But that takes some time. Usually if we give it say 15 minutes or so, there should be a color change. Currently if you come close or if you have seen the wafers, even like there were some in your kit that you got, so they have like a silvery shine. But then once an oxidized layer forms on top, although it's transparent, you actually can see in naked eye some different color changes as you hold it against some light reflection.
So this is a lab operation. We don't need the 8 or 12-inch wafers in succession, thousands of them. Those equipment have very high power, expensive, and what do we do with hundreds of wafers, right? So we cut small pieces, we oxidize, we do our processing. Most research labs do that. And this process is manual. You can get fancier automatic loading as well. It's just a matter of taste and money, if you will. And we have gas equipment here.
Centralized here from one room. Yes.
Right. So we have a central gas distribution in this facility, but for some specialized gas, for instance, we use ultra-high purity nitrogen and ammonia sometimes in this process. That's why this is have a separate.
Someone might be outside. Just ask him because he wanted to show
this. Is what. So what we'll do is we will start pushing this, and then you will see basically this material when it's pushed in, and about half an hour later, as I said, I think probably there's about 20-30 nanometer oxide already on it. But we will show you some already oxidized wafers to continue, because if you do every process fully, we will not be out of here for half a day. Okay, so that's the time management issue. Any questions for this piece of equipment you have? I mean, obvious safety, I mean, this is not very hot because this is insulation, there's special insulation, but with something like this, hot thing, you need to be aware what you're doing. Don't touch everywhere. You can burn yourself. I think it's not too bad around here. This is quartz. This is silica crystal qualities. So basically quartz crystal, and then that's very inert. So the tube itself is silicon and oxide only. So we are essentially forming the silicon oxide that we have on chip, but that tube itself is silicon oxide. So that's why we need to keep in silicon oxide for purity and cleanliness. In fact, if there was another material on the, if you had another material on the tube, and it is overheated, that material could have transported itself onto wafer, as the gas carries some atoms, and you could have actually contamination. So depends on what you do. And also, this is pure dry gas. If you are, sometimes you need to pass gases through bubblers and things. So the gas distribution things needed. Also notice an alarm here in case you are using dangerous gases. It needs to pick up. So safety is always important in facilities like this. But this is fairly innocuous, fairly easy experiment, because all we're using oxygen, and even if we have oxygen in the room, you'll be only happier, I guess.
Silicon dioxide can form this kind of glass, like the glass tube itself is silicon dioxide, you said?
Yes, this is the quartz crystal. This quartz crystal, the actual tube is crystal quartz. I mean, that's why it's completely transparent.
Okay.
What we form isn't pure crystal. I think it's mostly amorphous.
It's fused silica.
Yeah, this is fused silica.
Basically quartz.
But the oxide we form isn't crystalline. I think it's mostly amorphous.
Oxide is amorphous.
Mostly amorphous. Because in order to have the quartz is 1700, 1800, I think something like that Celsius, you need to rise up to that temperature.
Oh, okay.
So it's very, this furnace will not stand that. So we have an atomic force microscope. We have probe station to probe the wafers. When wafers are whole, you can all come in. When wafers are whole, not cut into the chips, how do you characterize, right? Because when it's all in the cases with leads and separate leads and wires, it's easy to characterize. Whereas when you are working with wafer, you want to be able to do quick measurements and see if everything is good. In fact, if you remember the wafers with their test chips around, those test chips essentially need to come down with these needles, specialized needles, and these needles are typically tungsten, because tungsten makes good ohmic contact to silicon. If you put aluminum and others, electricity doesn't immediately pass into silicon, and there's some differences in energy levels that prevent it. So these things basically are stable, and you can get these chunks, and there's another one, this is another one. This is high frequency one. You can see a high frequency measurement system is attached to this. This is basically measures up to 26 gigahertz. This is for extremely high velocity devices, satellite communication, and those measurements are very precise. They are very difficult measurements. They need this expensive and specialized conduits to be able to, and whereas you can have lots of probes in the DC or low frequency characterization, and high frequency characterization, you need to have very precise probes, so that, because high frequency signals don't go into the wafers immediately, you need to have impedance matching. If you don't have impedance matching, most of the signal will reflect back. So that sort of thing. So these are expensive equipment per se. So we have an atomic force microscope here. This one is a novel microscopy method. And essentially what this does, and then there's a picture here on the display if you'd like to see it. So what it does, it is essentially how a blind person uses a stick to scan and have a feel about the environment. We have an extremely sharp tip on a cantilever, goes and scans the surface, whereas the laser light is reflected off the back to monitor the slight height changes. So interferometry is used almost like interferometry, like features, which is the most accurate distance measurement, interferometry, which is what telescopes uses and everything. So similarly, we can track the minute nanometer changes. For instance, over here on the screen, if you come up here, there's some old patterns I picked up. These are not very good things, but this is 10 nanometer scale here, and that's 35 to, this is 60 nanometer scale. So whatever the things that were on the wavy stuff is there, it was was covering the surface with about 30, 40 nanometer height changes in that picture. So this is basically our electrical characterization room. We have other instruments coming in as we go on speed. We are not finished with this room. So in a minute, we'll get started with our lithography process. So remember that we take the wafers, we oxidize the wafers. That's always the step one, for more or less. Depends on some applications may need specialized starters, but when you do the oxidation, next you need to do patterning. So this is our pattern. Please come in. So, can we switch off the lights on this one? I think we should. I don't know why I think it's automatically coming on. If you come in towards me, okay. So yeah, if you can stand by the here. So the reason this room is dark and only you can come in, my partner. Yes. The reason this and you can also close the door if you will. This is because we have photoresist here. Let me show you photoresist. It is in a yellow bottle because this is light-sensitive, sticky material that covers the surface. When the surface is covered, it looks like this. You need to come up because I can't come up to the white light. So it is purplish, pinkish. Okay. The reason it's purplish pinkish because the wafer that we use had already oxide. That wafer looks like this. Let me show you an oxidized wafer. If you can flip that light for me, that is okay now. Yes. So I show you oxidized wafer. Can everybody see that? So that oxidized wafer is part of that wafer. We chop them up. The scriber tool you got does it. Can you see how flat it is? Because this is a crystal direction. Because this is 001 type of wafer or 100 wafer. If I cut rectangles are easy. I cannot get angles on this one easy. Okay?
Now, do you buy them oxidized like that? Or
Yes. You could see that entire 8-inch wafer here.
Yeah.
Entire wafer. Here's another piece of it. It's already cut into quarter from this bit. So we are only using a quarter of it yet, as of today. Okay.
How much do those wafers cost?
Oh, they are actually cheap if you buy bulk, but per wafer, a batch like this, depends on it. Much like other commodities, some people have more, they want to, I think something like that, big wafers like that, I don't think it will cost more than $500 like this or cheaper. But if you buy smaller wafer size, they are cheaper. And also, if you buy them other materials, gallium arsenide, much more expensive. In fact, gallium nitride, which is a wide bandgap material, semiconductor, which has all those blue LEDs, one wafer, 1 inch could cost about $2,000. Only 2-inch wafer. Okay, so what happens is, so we have these pieces. Okay, I will show you how we make the photoresist. You can come all the way to my back if you like, a couple of yours. So here's a spinner tool. So as you can see, we have a spinner tool. What we do is we put one of these wafers right here. This has a vacuum chuck so that the vacuum holds the wafer, and this thing starts rotating, and I show you, it won't work because we don't have the vacuum on, but basically this will rotate. It rotates up to 5,000, 6,000 RPM, very fast. Typically we deposit at 3,000 RPM. You can see it splashes to the edges, and then about 30 seconds later or so, you have these films. Then you need to bake them here at about 120 degrees for at least 2 minutes to 10 minutes, depends on what photoresist you have, how hot it is. And then they will be ready to use. Now, they are nothing special except silicon covered with photoresist. The reason I'm dark because they will be exposed to daylight, they will start interacting. So now we'll all turn back our backs to look at this machine which is behind you. This is where our mask aligner. Can everybody see the lamp actively on? Yes. Light is on, and then we have this light fixture is going to be exposed through this mirror into this surface. So I have here my mask. My mask is looking like this. So these are dust sensitive materials. So here is a mask material. This is silica. On the other side is the chromium. So it's a metal covered glass that somebody does already lithography using probably E-beam to, if it's very fine features. So you do another lithography system to prepare it. Once this is prepared, we need to mount this, and we mount this mask right here. There's a mask holder, and this thing holds on to the vacuum, this mask pattern. I'll show you the pattern that we will expose today. Can everybody see this pattern? These are chunky big rectangles and features. We are not going to show you that because you couldn't see it, and then we didn't hook up the monitors yet for the large display. So I'm going to get a mirror display here with a large camera so that students can always see this. But it's going to be easy for you to see. This pattern will be transferred to our wafer. Well, we are only going to use a small piece, right? I can put the entire 3-inch wafer. Only limitation of this research grade system is, in fact, it's not only research, but it's an older system. It can do only 3-inch wafers. What does it mean? Modern semiconductor processes wouldn't work here because they are 8-inch, 12-inch, etc. But it's okay. I don't need thousands of chips. In this 3-inch wafer, I could make hundreds of chips already if it's small enough. So this is hold. I'm going to put the sample. I'm going to put my sample in a minute here. Yes. So what I'm going to do is I'm going to take this one. And I'm going to take my tweezer. Can everybody see what I'm doing? If you can move a little down, if anybody, okay. So I'm going to put my sample here, which is this one. And it will go somewhere in this stage. It's blank. Because it's blank, I don't need to worry about, let me just put this one here. So can you also lower the sash? This has an alarm if the sash stays open too long. Okay, so what's going to happen, I'm going to push this in. So it's going under the mask. The mask and the sample is not in contact. What I'm going to do is, I'm going to increase the stage height, which is this thing. It pushes the stage up. And I'm going to bring the stage in contact. And I'm going to make sure that it is going all the way. So what's happening now, the sample is in firm contact with the mask. So there's no shadow. Because if mask is here, sample is here, shadows will develop. Even though light comes down, it's not perfectly rectangular beam, right? Flat beam, there's little angular light travel. Some beam parts are traveling like this, some are like this. So I will get lots of shadow effects. But bringing sample and contact is research okay, but if you do in real industry, you can't do it. Because the mask will erode, samples will get dirty, and then you will spend a lot of time. In the real world, what was it? There's a projection system, a lot of expensive lenses, and the samples move, keep moving, next one, next one, next one. A flash of light, next one, a flash of light. They are for speed, we are for accuracy. So this one we will expose actually 35 seconds. The reason we'll expose 35 seconds is because our lamp isn't necessarily very powerful. We go to a 500 watt, this is 350 watt, and this lamp appears to be in the last leg of its lifetime as well. So it's a little lower output. So what I'm going to do is this generates the light, and I'm going to say expose, and this is adjusted for 35 seconds with a dial, hand dial here. Watch now. It moved in, lens, the shutter has moved off the pathway. What you are seeing is the UV light, 365 nanometer light. So it's UV light. We shouldn't really stare at too long, but it's not too bad. It's the off diffuse light. But it's actually, this system is quite hot at the back, and it has nitrogen purging and cooling it all the time. And it's alarmed, if the nitrogen is lost, it will shut down itself to protect. This is mercury lamp, in case you are wondering. And it's very common in this process. So it exposed for 35 seconds. Now that is exposed for 35 seconds, I will now go in the reverse order. What was it? I'm going to separate the contact mode, and I'm going to lower the stage. I'm going to take my sample, and my sample doesn't look any different to what it was before. All it did, it received light. But the parts that are received light in the open areas of the mask have chemically actually broken down to smaller molecules, and it will be washed away in the actual process. I will let you guys take over from here because they're starting to go to the plasma now.
I will do the developing.
Yes. Okay. So you can take off from here the solution.
This is it.
Where is the development? It's all done.
Yeah,
Okay.
as in the-
So we did, I think, what last time was it 25 seconds?
20 seconds.
25 seconds. Yeah.
It's a bit bigger away. Okay, hi folks, and let's do the developing. And it's pretty simple. This is only the water. That was left. Anybody has a timer or something? Help me for about 20, how many seconds? 20 seconds. 20 seconds. Let me know when you're ready. Yeah. Press start. Just shake it a little bit. Let me know. Yeah, 20 seconds. Ready? 4, 3. Great. Now is water.
What solvent is that you use for the development?
Well, I don't know what they put in, and because we have different kind of developers, and for this time, I probably need to ask Hassan, come here and see the pattern. Can you see the pattern? See it? So anybody stand at backside, you can come and check.
Oh yeah, no, I saw it.
Okay. So. Great. And I need nitrogen to blow it dry. Yes, over there. Normally, oh, be careful. We have HVAC at this side. And close this one a little bit. Oh, this one is not fully.
You can turn that light on.
Yeah.
There's no problem.
Oh. What?
You're drying it?
Yeah, we're trying it. Blowing out the nitrogen and remove all water.
The agent step. Did you do the agent step?
No. So you will do that, right?
Yes,
If
yes.
you're That's good enough. Come on, guys, and take a look. Is that good?
Since all of them are wearing gloves, they can actually even hold the sample.
Yeah, you may.
Because there's nothing harmful in the sample anymore.
Yeah, because there's only for the developer.
What did you use for your developer?
Yeah, take a look. What?
What did you use for your developer?
I need to ask
Great question.
Yeah, great question. So because they.
Been there, done that.
These are the buttons, right? Yes.
Yeah, that's the pattern Dr. Kaya did.
I think it depends on what they use initially for the one.
Cool, right? Oh. All right, here we'll. Normally I just turn it up. turn them off. So I believe Hassan will do the etching.
So,
Good.